Hello, welcome to the class on Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Setramim. So in this class we'll discuss about the slot antennas. First, let us consider what are the possible applications for slot antennas. Actually, all the slot antennas are of low profile nature, and you can use this kind of antennas for flush mounting, such as in high-speed aircrafts. So the question is, how do we analyze such kind of slot antennas? So slot antennas can be analyzed from the complementary structure of slot antenna, which are called strips, like dipole. Dipole is a complementary structure of slot antennas. So we have already discussed on the dipole antennas. So now the complementary structure of dipole antenna is a strip slot. It's a slot. No, it's a slot. We'll see what is the complementary structure later on. So if we know the properties of dipole antennas properly or wire antennas properly, we can easily infer what is the antenna properties for slot antennas by using some principle called Babinese Principle. And this principle is basically used in optics, but Henry Booker actually extended this for applications in antenna. From there we can find out the input impedance of the slot antennas, and the patterns can be easily found out from that of the complementary structures like dipoles, wire or strips by applying the duality theorem. We have already discussed what is duality theorem. So let us look at what is Babinese principle in optics. So this principle basically says that the field at any point behind a plane having a screen. So we are considering the field which is behind a screen, and if you add this field at the same point, when we use the screen, second screen is a complementary screen. We first use a screen and actually find the field behind the screen, then you replace the screen by a complementary screen and you find out the field behind the screen of this complementary screen, and you add those two, then you'll actually get the field when there is no screen present. So two cases. First case is you put a screen and find the field behind the screen, and you, in the second case, you put a complementary screen and find the field behind the complementary screen. Add the field you have found out in first and two cases, it will be equal to the field when there is no screen present. So this can be understood from this diagram here. We are considering three cases. The first case, you put a screen here. This plane is called plane of screen. The plane at which we are putting the screen is called the plane of screen. We have a source here. Now this source is sending out light, and when we put a screen here, it will form a shadow here. So the plane of observation is here. Plane of screen is PS, plane of observation is PO. We have a source here. Since screen is put here in the plane of screen, we'll have a shadow at the plane of observations. So at the plane of observation, you find the field in the first case. So in the first case, you find the field at plane of observation. Let us denote that as Fs, field for the screen, or it will be equal to F1, which is a function of x, y, and z. So in the second case, we have the same source, but replace this screen by a complementary screen. So we have a screen here, we have a screen here. There is no screen at the point where we have at the place where we have the screen in the previous case. So this looks like a complementary screen. So now in this case, since you have a complementary screen here, there will be shadow here and shadow here. You find the field at this point of observation. We'll call this field at the point of observation for second case as field for the complementary screen, and it is equal to F2, let's say, which is a function of x, y, and z. And in the third case, you have a source, but here at the plane of screen, we don't have any screen, and we just observe the field at the plane of observation PO. So now let us call that field as FNS. because fill for the no screen, and we'll denote it by F3XYZ. Because of this Babinese principle, there is some relation between this F1, F2 and F3. What is the relation? F3 should be equal to F1 plus F2. So that is the Babinese principle in optics, and this principle is extended for the case of antennas by Henry Booker in the year 1946. So in the antenna analysis, if the first screen is a perfect electric conductor, the complementary screen for perfect electric conductor will be perfect magnetic conductor. PEC should be the first screen, and second screen, which is the complementary of PEC, should be PMC. Then we can extend this Babinese principle for the antenna analysis, and this can be done, the analysis can be done with the help of transmission line analogy. We'll see that in the next slide. So we are considering the case where you have incident electric field. Incident electric field, I'll denote it by EI. So, and here at this point we have an infinite screen, and the admittance of this infinite screen is denoted by Y1. So when this incident electric field hits this infinite screen, some of the field will be reflected back. We'll denote that by ER, and some of the field will be transmitted. We'll denote that by ET. This is the original problem we're considering, but we can take an analogy for the transmission line. So this original problem, we can actually take an analogy case for the transmission like this. So here what is happening? You have incident wave of voltage Bi, and this is the transmission line. This transmission line is having a characteristics admittance of Y0. The characteristic admittance of this transmission line is Y0, and assume that some wave is incident on this transmission line. Bi is the incident wave. So we have a sun admittance here of Y1. So this incident wave, when it reaches at this sun admittance, some of the signal will be reflected back and some of the signal will be transmitted. The voltage which has been reflected will be denoted by BR. Voltage which has been transmitted will be denoted by BT. From your basic undergraduate courses on microwave engineering, you may be knowing that we define some parameters called reflection coefficient, transmission coefficient. Reflection coefficient is the ratio of the reflected wave divided by the incident wave. So that's a ratio of BR divided by BI. And transmission coefficient tau, we usually denote reflection coefficient by capital gamma, transmission coefficient by capital tau. That is the ratio of the transmitted wave divided by the incident wave. That is BT divided by BI. So now in this case, let us try to find out how much is the reflection coefficient at this point here. We'll denote that by capital gamma. Capital gamma reflection coefficient, you know that it is Z load minus Z0. Z0 is the characteristic impedance of the line. ZL is the load at this point. Looking at this point, how much is the reflection coefficient? So that would be ZL minus Z0 divided by ZL plus Z0. So this will actually convert this impedance into admittance, because such kind of analysis where you have a parallel shunt admittance, it's easier to analyze in terms of admittance than impedance, because you know that when you have a shunt connection of two admittance, it adds up. No? So if I want to convert this impedance into admittance, I just take 1 by YL. 1 by YL will be equal to ZL. 1 by Y0 should be equal to Z0. Just replace it here. Then the relation for the reflection coefficient will now become Y0 minus YL divided by YL plus Y0, where Y0 is the characteristics admittance of this transmission line, YL is the load admittance, looking at this point. So looking at this point, when you look at it, there is a Y1 here, there is also Y0 here. So they are in parallel combination. Y1 and Y0 are in parallel combination, and these are the admittances. So when you look from here, the load admittance would be Y1 plus Y0. just replace YL by Y1 plus Y0, then you get the reflection coefficient as minus Y1 by Y1 plus 2Y0. So far so good. Let's look at the next slide. Let's say we're interested in the transmission coefficient. That's the ratio of the transmitted wave divided by the incident wave. And you can easily prove that transmission coefficient is equal to 1 plus gamma. That's a basic standard formula you use in microwave engineering course in your undergraduate studies. So we have the expression for capital gamma. I just replace that. Then simplify it. What we are getting is transmission coefficient for this particular transmission with a shunt admittance, transmission line with a shunt admittance is 2Y0 divided by Y1 plus 2Y0. Okay, so now we are ready for applying the Babinese principle for antenna analysis. So here, as I already told you before, in the first case, we'll consider screen is a PEC infinite screen. In that case, you calculate the transmission coefficient. Let us denote that by tau 1. That is for the first case. 1 is for the first case. Tau 1 will become 2Y0 divided by Y1 plus 2Y0. Y1 is the admittance of the PEC infinite screen. In the second case, replace this PEC infinite screen by a PMC infinite screen because they are complementary structure. In that case, let's assume that the surface admittance for that case is this admittance has been written twice here. We need to remove only one should be here. Okay, so PMC infinite screen, let's assume that surface admittance is Y2. In that case, the tau 2, the transmission coefficient for the second case will be 2Y0 divided by Y2 plus 2Y0. According to the Babinese principle, let's say if the screen were not there, that means this Y1 will not be there. If Y1 was not there, then how much would be transmission coefficient? Transmission coefficient will be 1. Nothing was there on the line. Wave was propagating. There is no reflection. All the signals are going in the right hand side. So transmission coefficient when this shunt admittance was not there would be equal to 1. So from the Babinese principle, tau 1 plus tau 2 should be equal to 1. We have the expression for tau 1 and tau 2. Put it here, simplify it. What do we get? So you have replaced the expression for tau 1 and tau 2 in terms of admittance. Simplify it. Cancel out the common terms in the left hand side and right hand side. Then finally what you are getting is 4Y0 square equal to Y2 Y1. So this relation is the Booker's relation for admittance. Henry Booker actually derived this for application for antennas. If you change this admittance into impedance, because we work in terms of impedance most of the time, so in that case just replace this Y0 by 1 by Z0, Y2 by 1 by Z2, Y1 by 1 by Z1. Then what you are getting is Z1, Z2 is equal to Z0 square by 4. Or you take the square root of this, square root of Z1, Z2 is equal to Z0 by 2. So when you take square root of two numbers, we call it as geometric mean. Geometric mean of Z1 and Z2, that is the surface impedance of the first case and second case should be equal to Z0 by 2. Where is Z0? Z0 is the intrinsic impedance of the surrounding medium. Look at this. This is the original problem. We have considered you have incident electric field, you have a reflected electric field at the infinite screen. Some of them are transmitted. This was the Y1 was the admittance. So now, what is the impedance of this free space? Free space impedance is around 377 ohm. So Z0 is actually free space impedance of the surrounding medium, which is approximately 377 ohm. So square root of Z1, Z2 should be equal to 377 by 2. We can apply this Booker's relation for finding the impedance for slot antenna. Once we know the, let's consider this simple example. We have already studied about the dipole antennas. So this is the structure of a dipole antenna. You have a upper arm of the dipole, lower arm of the dipole. We put the dipole at the center, and we are actually connecting this dipole with a source at the center, so this dipole will start radiating. You find out the impedance for this dipole. We already know how to find the impedance for the dipole. So I know what is the impedance of this dipole. I denote it by ZD. So now you consider a complementary structure where you have metals everywhere, then you have a slot here, and you are feeding this slot with a source, AC source at the center of this slot. This structure and this structure are complementary. So now we apply the Booker's relation, find out the impedance for the dipole as ZD. We want to find the impedance for this Z slot antenna. We can easily do it. ZS ZD is equal to Z naught squared by 4. Z naught is the wave impedance for the intrinsic impedance for the free space. So ZS will be simply 35,476 divided by ZD. So once we know ZD, the impedance of the dipole antenna, I can always find the impedance of the slot antenna. We don't need to do any kind of derivation. Just find out the dipole antenna impedance. Just use this Booker's relation. Then you can find out the impedance of the slot antenna. So that's very convenient using this relation, Booker's relation. Usually ZD is complex number. So if ZD is complex number, ZS will also be a complex number. So this relation holds true even for complex number. When ZD is a complex number, ZD is usually complex. So we have got the input impedance of the slot antenna using the Booker's relation. I also want to find the far field radiation pattern of this slot antenna. Here also I don't need to do any derivation. I'll use the previous knowledge of duality theorem and find out the far field radiation pattern of a slot antenna. Let us consider a half wavelength dipole antenna, and it has a far field radiation pattern expression like this. This relation has already been derived in lecture 18. This portion inside the third bracket will give the radiation pattern. This is almost like constant. So cos of pi by 2 cos theta divided by sin theta. Similarly, for the E theta and H phi also will have similar kind of expression. So we have the far field radiation pattern for a half wavelength dipole. Let's say if I want to find the far field radiation pattern of a half wavelength slot antenna, how do I find it? I just apply the duality theorem. We have already spent more than one lecture on the duality theorem. So what do? We replace the dual terms. For example, eta is a dual term. When I want to replace it for the slot antenna, I will replace eta by 1 by eta. I know is for the dipole antenna. For the slot antenna, IM, magnetic current, and other terms are all same. Similarly, here also I will replace I naught by IM, and all other terms are same. Just don't forget that when I change from magnetic field to electric field, I have a negative sign here. That was from the duality theorem. We have spent a lot of time on duality theorem before. Now I think by now you are expert on duality theorem. So eta has been replaced by 1 by eta. I0 has been replaced by IM. When I convert this magnetic field into electric field, I put a negative sign here. So I have got the radiation pattern, I have got the impedance. Once I have the radiation pattern, I can also find out other antenna parameters. That's about the slot antenna. There is another kind of slot antenna which is very popular, which is called slotted waveguide antenna. Basically, on the waveguide wall, you have many slots, and from there you can form antenna also. You can form antenna array also. And another name for slotted waveguide antenna array is called traveling wave slot antenna arrays. So this is actually a slot on a waveguide wall. This is a rectangular waveguide. Dimension is A along the x-axis, B along the y-axis. So now this is the central line of the waveguide. I have a slot here which has been offset by delta from the central line and offset as x1 from the edge of the waveguide. So such kind of slot will start radiating. Signal inside the waveguide was guided wave. No, it was confined inside the waveguide, and you know the rectangular waveguide. Usually T10 mode is the dominant mode when A is greater than B. So now inside on the walls of the waveguide, if you put a slot like this, then signals which was propagating inside the waveguide will start coming out of the waveguide and start radiating. See, we have an equivalent circuit for this slot on the waveguide walls. This is a simple equivalent circuit. You can derive it actually. So this G is actually normalized G. Let's say Ys is the shunt admittance of the slot in the waveguide wall. Y0 is the characteristics admittance of the waveguide mode. Then G is basically Ys by Y0. So G is the normalized shunt conductance of the shunt slot here we have on the waveguide walls. So this is only one slot. We can have many of them. Then we can form antenna array. Let us try to find out what is the relation for finding this normalized shunt conductance. Normalized shunt conductance can be found out from this relation. G is equal to, it has been derived by Stevenson, and I have given references. From the references you can find out. One book is there, A.J. Sangster. He has a book on the slot antennas. So Stevenson has derived this G is equal to 2.09 lambda G A divided by lambda 0 B. Lambda G is a guided wavelength. If you are considering T10 mode, guided wavelength can be found out as 2 pi by beta 10. Beta 10 is square root of beta square minus pi by A whole square. And usually this guided wavelength is always longer than the free space wavelength. Free space wavelength is lambda naught. Inside the waveguide, the guided wavelength is always longer than the free space wavelength. So we have a guided wavelength lambda G here divided by lambda naught. A and B are dimensions of the waveguide. Cosine square pi lambda naught divided by 2 lambda G. So these terms are independent of the slot dimension. No? These terms are parameters of the waveguide. Lambda G is for the dominant mode. A and B is the dimension of the waveguide. Lambda naught is the operating frequency. From the operating frequency you can find out what is lambda naught. But the most important term we have here is sine square pi delta divided by A. Delta is the offset from the central line. See this slot center, how much it has been offset from the central line of the waveguide, that is your delta. So this delta is a very important factor for determining G, which is the normalized conductance. Delta can be also expressed as A by 2 minus x1. x1 is offset from the S, and delta is the offset from the central line. So at the central line, what is value of x? X is A by 2. So A by 2 minus x1 is the also can be expressed as a delta. So this parameter is going to decide what is the value of G. When you keep on increasing it, it's going to increase. When you keep on reducing it, it's going to decrease, because this is a sine function you have here. So now that was a single slot, but single slot the radiation is not very good. So usually for the waveguide, slotted waveguide antenna, we have many slots. And usually this slot, look at this slot here, this slot and this slot are staggered. No? So you have a slot here, you have another slot here, you have another slot here, you have another slot here. So you'll have many slots, but they are not put on the same side. If they are put on the staggered fashion, so that radiation from such kind of slotted waveguide is really good. So this is a rectangular waveguide. This is the x, y, z coordinate system. This x-axis, y-axis, z-axis. Let's say we have a T10 mode, which is incoming mode in the waveguide, or it's already propagating inside the waveguide. This is the dominant mode, and assume that at the other end of the waveguide, you have a match termination, so you don't have any reflection from here. So signal is coming from one of the end of the waveguide, and then from the other end you have a match slot. And this is the main beam direction. So this is theta, so this is pi by 2, so pi by 2 minus theta is this angle here. So this is the direction of the main beam. So now, as we already know that a single slot is equivalent to a shunt conductance. So this is the waveguide, this is transmission line model, and this is the waveguide, and let's say this waveguide has a wave impedance of Z0. In that case, for the match termination, Z load should be equal to Z0. And for the first slot, you will have a shunt conductance, normalized shunt conductance as G1. For second slot, you will have G2 and so on. If you have N slot, the last one will have shunt conductance of Gn. The distance between the two slots, center to center, is from here to here is D. So we have a spacing of D. So now this looks like an antenna array. So if you want to find out the radiation pattern of an antenna array, what do? You first find radiation pattern of a standalone element, and you multiply with the array factor. So array factor becomes a very important criteria for deciding the radiation pattern of an antenna array. So for this case also, we want to find the array factor. Once we have the array factor, we can easily use the pattern multiplication principle and find the radiation pattern of this slotted waveguide antenna array. And in order to find out the array factor, we need to know the location of each slot. Then we can easily find out what is the array factor. Let's say you consider any ith slot. This is the first slot, I will become 1, second slot I will become 2, third slot I will become 3. You will have many of them, but I have just shown 3 of them for easier illustration. So now you consider any ith slot, then what is the distance of this ith slot from the ace of the waveguide? We'll denote it by xi. What is the location of this slot along the y-axis? Is B. This is on the waveguide wall. This distance is B. So we have a B y hat, and this displacement from the S of the waveguide, we'll call it xi. And the first slot would be displaced at a distance of D. Second slot would be displaced at a distance of 2D, 3D, and so on. That's why ID, Z hat. I goes from 1, 2, 3, 4, and 5, and so on, natural numbers. So xi is the offset distance of the ith slot center from the waveguide side wall. ID is the distance along the z-axis. This is the z-axis. First one will have D, this will be 2D, 3D along the z-axis. Along the y-axis, all are at the same location, B, Y hat. So height of the waveguide is common for all slots in the waveguide. It will not have any influence on the radiation pattern of the slotted waveguide, and it will not contribute in the calculation of the array factor for the slotted waveguide antenna array. So we can neglect it. So I can rewrite Ri is the ith position of the slot center is xi x hat plus id z hat. So once we have this, we can calculate the array factor. Array factor is simply 1 plus A1 is the excitation for the first slot. Let's assume that the first one is excited with the amplitude of 1 and it doesn't have any phase delay. Second one is excited with amplitude A1 and there is a phase delay which will be counted, taken care of by exponential j sigma 1, and A2 plus A2 exponential j sigma 2 and so on. The nth slot will have a amplitude excitation of an minus 1. Exponential j psi n minus 1 will give us the phase shift. So AIs are the field excitation amplitude at the ith slot. What is this phase shift here? Psi I. Psi I would be beta dot Ri minus beta 1 d plus pi. What is this? Minus beta 1 0 d is basically, now the waveguide, inside the waveguide the field is propagating, dominant mode is propagating. As it moves a distance d from one slot to another slot, so the fields which are propagating T10 mode, it moves from this slot to another slot, this slot to another slot. How much is the phase shift due to motion along the z-axis? That is minus beta 10 d. Another thing is that now this is not on the same side, it has been staggered. How much is the phase shift from here to here? It's around pi. So we have minus beta 10 d plus pi. What is beta I d cos theta? Wait 1 second. What is beta dot I? Beta dot Ri, that's also we need to find. What is beta 10? Beta 10 is square root of beta square minus pi by a whole square. Beta is 2 pi by lambda. Lambda is the wavelength for free space. We have already told pi is the phase shift due to the slot staggering. What is beta dot Ri? That's what we want to find out. We already know what is Ri. What is beta? Beta will have x, y, z component. So x component of beta will be beta sin theta cos phi, y component will be beta sin theta sin phi, and z component will be beta cos theta. And Ri is having only x and z component, xi, xz plus id, z hat. So when we do the dot product, we'll simply get beta xi sin theta cos phi plus beta id cos theta. So psi I will turn out to be beta xi sin theta cos phi plus beta id cos theta minus beta 10 d plus pi. So we have psi I now. And most of the time we actually consider radiation pattern for E plane and H plane. Here we'll consider radiation pattern for YZ plane. In that case, phi will become pi by 2. Phi is equal to 0 is XZ plane, phi is equal to pi by 2 is YZ plane. So in that case, phi is pi by 2, cos of pi by 2 will become 0. So this term also goes away. So simply what we have is psi I is beta id cos theta minus beta 10 d plus pi. So now we can find out the error factor. Error factor is 1 plus a1 exponential j psi. You can observe that all the psi I are so psi I is this, psi I is this. So we can find out the error factor as 1 plus a1 exponential j psi plus a2 exponential j2 psi plus an minus 1 exponential n minus 1 psi, where psi is beta d cos theta minus beta 10 d plus pi. So I should actually have an I here. I'll change that later on. So this is a cumulative effect, so I should have an I here, I should also have an I here. This is for the ith slot, so I should have I here also. I should also have an I here also. I is the ith slot. I can take any value from 1 to n. And if I write array factor as 1 plus a1 exponential j2 j psi plus a2 j exponential j2 psi plus and so on, then last one is n minus 1 exponential j n minus 1 psi. In that case, psi will become psi I will become I times psi. And what is psi in that case? Psi will become beta d cos theta minus beta 10 d plus pi. And you know that man beam is for psi is equal to 0. You can easily find out man beam location by putting psi is equal to 0. But we also have primary lobes, primary lobes, and you know that from antenna array theory, primary lobes occur at psi is equal to 2m pi. So if you equate psi is equal to bd, psi is actually bd cos theta minus beta 1 d plus pi equal to 2m pi, where m is a natural number from 1 to m, capital M. In that case, I can find out the value of d. I can find out the value of d. So I can replace this beta by 2 pi lambda, beta 10 by 2 pi by lambda G10. Then I can simplify it. I can find a value of D. So this relation will actually give me what should be the value of D according to our requirement. I need to design a slotted waveguide antenna array. D is the criteria. No? What is the distance between the one slot to another slot? D can be found out from here. 2m minus 1 divided by 2 lambda G10 lambda G10 cos theta minus lambda. So let's say I want to have theta is equal to 0. Theta is equal to 0 means, what was theta? Theta was this angle here. So if theta is 0 means beam is along this direction. Theta is equal to pi, also beam is along this direction. So for theta is equal to 0, D is this. Just put cos theta is cos of 0 is 1. Similarly, theta is equal to 180 degree, then cos of 180 degree. Just here put cos of 180 degree, then we'll have this relation here. You can find out when you want to have the main beam direction along theta is equal to 0 or theta is equal to 180 degree. You can find out what is the value of D from this relation here. You can also observe that D becomes infinite when this term here in the denominator is equal to 0. Lambda G10 cos theta minus lambda is equal to 0. In that case, cos theta will be lambda by lambda G10. So you can find out what is the cos theta when distance between the slots are at very far away distance. So the design for slot spacing D can be done from this analysis we have done. So in the slot antenna, we have considered a simple slot antenna, which is a complementary structure of dipole antenna or wire antenna. And we have also considered slotted waveguide antenna and antenna array. We have found out the equivalent circuit, and we have also found out what is the design criteria for this slotted waveguide antenna array. So that's all about the slot antenna. In the last part of this lecture, I actually want to share with you guys the slot antenna and arrays we have originated from our research group. And there are two PhD students. One is my 9th PhD student, and this is the 10th PhD student. They have been working in this area for several years, and they have already proposed several slot antennas and arrays especially for full duplex radios. So in wireless communication, most of the time you do one-way communication. If you do two-way communication, that means you simultaneously transmit and receive signals, then the capacity will increase twice. So you can have higher capacity using full duplex radio, twice that of the usual conventional one-way communication. When you have two-way communication, you are transmitting as well as receiving the signals, then you have a full duplex wireless communication. There the capacity will increase twice. Your speed of communication will become twice in the layman term. So we have actually designed some slot antenna and arrays for full duplex radios, and most of the antennas we have designed were for dual circular polarized case. We have designed not linearly polarized, but we have designed dual circular polarized slot antenna arrays for full duplex radios. I'll just briefly mention you three of them. The first one is the dual circular polarized slot antenna with split ring resonator based novel meta surface. And the second one is series FET dual circular polarized slot antenna with metallic reflector. And third one is dual circular polarized slot antenna with 8 safe slots with interdigital capacitor. So first one we have employed meta surface. Second one we have employed metallic reflector. We have already seen what is the effect of using metallic reflector. You have already known that when we analyze the reflector antennas, when we have a flat sheet reflector or corner reflector or parabolic reflector, we have seen that gain increase significantly. Here also we try to analyze dual circular polarized slot antenna by employing metallic reflector. In the first case, we use meta-surface meta-pop split ring resonators, and in third case we'll use interdigital capacitor. So in order to improve the performance of all these antennas, we use different kind of techniques. First is meta-surface, second is metallic reflector, and the third one is interdigital capacitor. Let us look at the structures. So this is the first structure we are considering, and this is actually you look at this structure here. This is a dual circular polarized slot antenna. This is the fit line. We have a fit line here. This is a slot. This slot is radiating. We are feeding the signals from these two slots here, two lines here, microstrip lines here. There's a substrate in between. This is a ground plane. We are putting a slot in the ground plane. We are feeding the microstrip line in the other plane. You can see a meta surface here. This meta surface is made up of split ring resonators. So now we are feeding this slot using this microstrip fit lines here, and we have actually achieved dual circular polarized antennas using this fit line to the slot we have designed here. And what is the purpose of this meta surface? See, basically, as I already told you, I want to use the same antenna for transmission and reception. So when I transmit and receive at the same time, there will be a lot of interference between the signals which are transmitted and received. So in order to reduce the interference, we actually need to have a very high isolation between the ports, transmitting port and receiving port. So we actually put this meta surface to increase the isolation, and after application of this meta surface, what we have observed is isolation is almost 20 to 36 dB. Usually most of the antennas have, see, until and unless you apply any kind of techniques here, this isolation will not be so good. So after applying meta surface, we have a very good isolation around 27 to 36 dB. And this antenna has a bandwidth, 10 dB bandwidth, which is the impedance, also called as impedance bandwidth, is around 28.52%. This is a broad antenna. Usually slot antennas has very good bandwidth. This antenna operates at center frequency of 6.45 GHz. And here we have considered two bandwidth. One is the impedance bandwidth. This impedance bandwidth is related to your reflection coefficient. So here your reflection coefficient should be based on reflection coefficient, your S11 should be less than -10 dB, so that this antenna works within the bandwidth of the operating bandwidth of the antenna. The S11 should be less than, amplitude of the S11 should be less than -10 dB. So you can find out the frequency at phase, frequency range for which this antenna is having -10 dB bandwidth. It's at the center frequency of 6.45 GHz, is percentage bandwidth is 28.52%. There is another bandwidth which is usually defined for the circular polarized antenna, which is actually the ratio of the let's say you consider ellipse. The ratio of the major axis and minor axis is called the axial ratio, and usually we have circular polarized antenna when axial ratio is less than 3 dB. So that 3 dB bandwidth, you can observe it for this circular polarized antenna. It gives a bandwidth of 8.9% at the center frequency of 6.54 GHz. And this antenna is very compact. The size is simply 1.58 lambda naught into 0.75 lambda naught into 0.024 lambda naught. This is a very compact antenna. Even after application of this meta surface, the antenna size is quite small. And as you know that all the metamaterial structures are subvalent structures, usually their dimensions of the order of lambda by 10. So it's a very compact antenna with a very good isolation. Gain was observed to be from 2.9 to 3.6, and as usual, most of the slot antenna will have bi-directional radiation pattern. It will radiate in both directions because of the slot. So this is the first antenna we'll be discussing, and it has been originated from our research group. And if you are interested in finding more details about this antenna, you can go to this link here. Then the second slot antenna which has been originated from our research group is called series PET dual circular polarized slot antenna array. So here you have a slotted ground plane. These are a slot. How many slots are there? 10 of them are there. The orientation is designed properly so that we will have a dual circular polarized antenna. And this is one single slot you have here. How do you analyze such kind of antenna? This is a power input to that. There is a fit line here. So I'll show you that. This is a fit line. This is a port 1, this is a port 2, this is a fit line. Look at the antenna from the side view. What you have, your fit network is here. You can assume that this is your microstrip plane, and you have a slotted ground. The slot is put on this ground layer here. This slot I have shown here, these 10 slots which are put on the ground layer. And we have a fit network like this with port 1 and port 2 circular shape fit network is there in this fit network. So now how do I analyze this kind of antenna? I have a power input to this one single alone slot. This is a power input, this is a power output, and whatever power has gone for radiation, that is power radiation. So you can define a parameter called gamma. Gamma is the ratio of your power output by power input, and it is equal to, this should be 1 minus S21 square. And usually if you take your gamma, which is the ratio of P out by P in, as 0.57 for an isolated antenna, so a ratio of P out by P in is 0.57, then what we observe is that when I give a signal at port 1, only the most of the power will be radiated from this first 5 antenna. When I put a signal in the port 2, most of the power will be radiated from these 5 slots: R10, R9, R8, R7, R6. This is the fit line, but the slots, corresponding slot will be S10, S9, S8, S7, S6. So it has been observed that 98.7% of the power is radiated from the first 5 slot. If you fit it from here, then first 5 slot will radiate. If you fit it from here, this first 5 slot will radiate. So this antenna performance isolation is from 25 to 45 dB, and the minus 10 dB bandwidth is 18.46% at the center frequency of 6.545 GHz, and the axial ratio bandwidth is 13.46% at the center frequency of 6.54 GHz. And as I already told you, power coupling coefficient was taken as 0.57. And what you can observe is this antenna has a very good gain. That is because of this series feeding here. We have a series feeding here. We are not having only one slot. We have a series of slot fit with a fit network. So because of this series feeding, this antenna has a huge gain. So look at the previous antenna. What was the gain? Gain was 2.9 to 3.6. But this antenna, because of this series feeding, we have here, it has a gain of around 8.2 to 9.5. And see, I have already told you this antenna also uses a reflector. Just like we have done the analysis in the reflector antenna analysis, we have a metallic reflector here which is placed at a distance Hg from the fit network. Because of this reflector, even if we have a slot here in the ground plane, there won't be any backlobe radiation. All the backlobe would be reflected back, so we have a unidirectional radiation pattern in this case. And because of this metallic reflector, also we have improvement in this gain here. After we fabricate this antenna without the reflector, gain was not this much high, so we put a reflector here, gain has been increased. If you are interested in this second antenna, which is also a slot antenna array, you can go to this source link and you can explore. We have one more slot antenna, and this is also for full duplex radio. We have a dual circular polarized slot antenna. We have 8 safe slot here, and they are oriented in a perpendicular direction, so that isolation is very good between the two antennas. This is a fit network. This is port 1, this is port 2, and as usual this fit network is in the microstrip plane and these slots are in the ground plane. And in order to improve the isolation, we have used interdigital capacitor here. This filter is a bandstop filter which will actually minimize the interference between the port 1 and port 2. So we have isolation within the bandwidth of the antenna around 17.6 to 46, and the minus 10 dB bandwidth is around 15.75% at center frequency of 2.293 GHz. Axial ratio bandwidth is 11.52% at center frequency of 2.1275. Antenna size is also quite small, 1.14 lambda naught into 0.91 lambda naught. The gain is 3 to 5 dBi, and you can observe that when I have a series fit antenna array, I have a huge gain along with the reflector. This reflector also gives in the gain improvement. Here the gain is not very high, and since we have not used any reflector, this kind of slot antenna will have bi-directional radiation pattern. And if you are interested, you can always explore to this source link here. That's all for this class. Thanks for your attention.